All right, well, welcome to part 2 of 8.7. Here we're going to look at the margin for our error in our estimation. So there's two ways to find the exact value of the area bounded from 0 to 2 on your graph. So let me walk you through the calculator steps here real quick. So what you want to do is you want to move this down, make the graph a little bit bigger. There we go. Hit second trace, ask for number 7. And so here is our equation. I put it into y1 and transferred it to y2, so it would be in red. But I have 1 over 1 plus x squared in y1. You got to give it a lower limit, which is 0, so just go ahead and hit enter. An upper limit, which is our upper bound 2, hit enter. And it calculates the area out perfectly. So that's where this number here is coming from. The second way you can do it is on your home screen. You can go, again, because we have it stored in y1, we can go math, number 9, 0 to 2, and we don't have to type in the fraction again. You can just hit alpha, trace, type in y1, and then we're going to integrate it with respect to x, and that too will find that decimal area right there. Okay, so that's how we can find it. Now, the error that we are going to look at here is the error for my midpoint, is that my midpoint was just a little short of what I have under this curve here. And it came out to be 0.000117. That's how far I'm off. So if I go my approximation by midpoint minus the actual area, I'm coming up a little short. It's a negative value. With my trapezoid approximation, I subtract the actual calculator version of the area. I come out to 0.0002355. Now, the observation that we're going to make here is we're going to look at, let's say, one rectangle to a curve. Okay? And our rectangle is done by the midpoint. That's where point P is. So if you were to draw the tangent line BC at point P, it's going to make two right triangles, BMP and CNP. And those two right triangles are equal in area. In fact, they're going to be congruent. So what we form now is AMND. That midpoint rectangle is the exact same area as trapezoid A, B, C, D. It's like we cut off this right triangle here and we spun it around 180 degrees until it landed right here, and it's the perfect match. All right, now the trapezoid AQRD is from our trapezoid technique. And what you're going to notice here is that if my curve concaves down, my midpoint is always going to be too, in this case, it would be too big. And here, my trapezoid, estimation is going to be too small because we are technically under the curve. And if it concaves the other way, then it's reversed. So the one thing I want you to notice is that my midpoint, again, trapezoid ABCD, is going to be slightly higher in estimation than our trapezoid technique AQRD all the time. All right, so that means midpoint is bigger, trapezoid is smaller. So your errors in your signs have to be opposite all the time. Okay, so in this particular case, in our shape here, our trapezoid area was bigger, and we subtract the original area, you get a positive. Here, the midpoint approximation was smaller, subtract the actual area, it's negative. If my curve is concaving up, then it's reversed. My signs will always be opposite. The next thing I want you to notice too is the size of the error. The midpoint rule is always about half, right around half of the trapezoid error. So if I took 2, 3, 5, 5 and I divided it by 2, I'm going to be really close to 1175, if you put all the decimal zeros in there and everything like that. So it's always, if you call it a 1 to 2 ratio. This is 1, this will be approximately double, or the midpoint half of the trapezoid, or if you want to say trapezoid is twice as big as the midpoint, excluding the signs, if you will. So you can kind of see that in my shape here. In red, that's my midpoint error, if you will. And in blue, that's my trapezoid error. And it definitely looks like the trapezoid is covering more space, more area than what's shaded in red. Okay, so that's, if we're looking for our error compared to exact area, that's always going to be a tendency. All right, error bounds. This definitely is not on the test, and I'm going to explain to you real quickly why. It's because you've got to find double derivatives to understand where this bound is at. So I worked out a problem, but again, it won't be on the test. But in case somebody wants to ask you what it is, you will understand that, hey, I've seen this before, you kind of understand it. So my error bound basically means is what's the lower and possible upper bound that my error could be? Well, because these two are opposite in sign, we're going to take its absolute value. So this error has to be less than or equal to b minus a cubed over 24n squared times, now get this, the maximum value of the second derivative of your function on your bound from a to b. So in our problem, it would be from 0 to 2. And for the trapezoid rule, my bound, again, could be positive or negative, but it has to be, my error has to be less than b minus a cubed over 12n squared times the max, again, of the absolute value of the second derivative on your bounds from 0 to b. Now, why would this be a problem? It's because, well, you got to take your function, then you got to take the derivative of it, and then you got to take the derivative of it again. Well, you could be asked to type this in and find the graph of where it's at. So this second derivative right here is actually the green graph. The graph in black, that's the first derivative. And then you would have to use your calculator to find that relative max, so you can plug that into this value here and multiply it to this fraction. Now, do we want to find these derivatives and have to do all these quotient rules that we're seeing here, chain rules, and it just becomes bigger and bigger, and it's just a nightmare? No, you don't have to. You can have your calculator find these numbers right here every single time. Okay? So let me show you in a calculator a really neat trick in how to find the graph of your first derivative and the graph of your second derivative. So I'm going back to my graph. If I go to y equals, okay, let's see, the first derivative was in black, so I'm going to do this in y3. You can go to second, check, math, ask for the derivative number 8. Okay, we're going to take the derivative with respect to x, and that's going to be an x as well. And inside, inside the parentheses, there we go. Inside the parentheses has to be our function. Okay, that's where y1 comes in. So I'm just going to put alpha trace y1. Put y1 in those parentheses right there. And if I hit graph real quick, there you can see that black graph that I created. If I go, let's see, we did the second derivative in green, so I'm going to go down here to y5. Again, hit math, number 8, graphing the derivative. Again, this is an x. Here, you're going to want to put in the first derivative graph, which was y3. So alpha trace y3. And again, we take the derivative with respect to x. And if I graph that, here comes that green graph. And now between 0 and 2, that's the area that's shaded there in red, I can ask for, okay, second trace, let's find the relative max. Now remember, it's always going to go to the first curve you plotted. So in this case, the first one I have turned on is y2. So you just hit the down arrow until the green graph shows up right here. And you can just go from 0 to 2. That will work. And it's going to find that high point right there. And there it is. So there's the 3.2299529 that I need for the formula. So that's this value right here being multiplied to 2 minus 0, which is 2. That's 8. 24 times the number of rectangles, 8 squared. Multiply that out. So what's that saying is that this bound for my error is always going to be less than 0.016822862. Could be a positive or a negative number, but if we take its absolute value, it has to be less than that. And so here's my trapezoidal error. And again, as you see, same number crunching concept with that formula. I crunch the numbers, and you can notice 0.0168, 0.0336. It looks like the number here in red for the midpoint error bound is about half of the trapezoid, or if you will, the trapezoid is twice as big as this error message here. Okay, so am I going to ask you these questions on the test? Probably not. If you check the reviews, I'm pretty sure they're not there. That's too much to ask for. All right, so that wraps up the errors.